Hi there, good afternoon, welcome, thank you for coming. We're thrilled to be here today at reInvent for the first Energy and Utilities track. I'm excited to have Jeff Davis from the Hess technical computing team with us today to share their experience in leveraging the AWS cloud to manage and process petabyte scale seismic data. My name is Sunny Sunkara. I'm an Enterprise Solutions Architect with Amazon Web Services. Today, we're going to have Jeff Davis share with us their story in managing and processing petabyte scale data on AWS. By the end of this session, we hope that you walk away with learning a bit about Hess, but also gaining insight from their experience around managing seismic data on AWS. You will hear about the challenges they faced and how they utilized various best practices with regards to data acquisition, archiving, and processing. We'll also get a glimpse into the technical architecture that was implemented. And finally, Jeff will share with us the testing and the results that they've achieved by taking advantage of the agility and elasticity of the AWS cloud. With that, I'd like to hand it over to Jeff Davis again to tell us a little bit about Hess and share their story.
Hello, everybody. I'm Jeff Davis from the Hess Corporation, and I'm going to talk a little bit about kind of our history of kind of technical computing a little bit, and then kind of talk about how we kind of migrated into the kind of cloud world. Hess is the Hess Corporation itself has been around for quite a long time. It formed from the merger of the company called Amerada Petroleum and the Hess Corporation. Amerada Petroleum was very much a pioneer in the use of seismic technology, and the Hess Corporation, which was founded by our founder Leon Hess in 1933 in New Jersey, started with a single truck and kind of forged these two companies together, and we gradually grew to add resources basically around the world. We were in Europe and Africa and South America. We basically developed around the world. In 2013, we decided that we wanted to focus in on really the exploration and production part of the business. And so we sold all our downstream assets and gas stations and refineries. And we've had some recent successes in South America and the country of Guyana. So we've had some real good results there. So kind of a diverse company with a long history, especially with technology. So Hess is really, we have kind of a thing at Hess where we talk about we want to be part onshore with the shale oil type exploration and production, and part offshore, part international, part domestic. So we try to really focus on developing oil and gas reserves around the world, but we try to focus on core assets. We are, we do a lot of work in North Dakota around the shale oil onshore, and we also do work offshore, like I said, in Guyana. And really, we use a lot of technologies to do a lot of this business, both IT technologies and kind of oil and gas drilling technology. So it's a really technological business. Just to kind of give you a brief kind of we talk about the word seismic, so I thought I would just, for those maybe who don't know what I'm talking about, seismic is just simply kind of like a sound recording. It's a recording. You've got these areas here that create sound, and then you have these areas here are called receivers, and they receive the reflections. So the process involves the sound, the reflections, and time. Time is very interesting point. The time that sound travels through materials tells you a lot about the materials. We look at things like round trip times and things like that allow us to tell us what kind of materials are down there. We're talking about very large areas, thousands of kilometers. A typical seismic survey might involve millions of records and then hundreds of terabytes. So there's very large amounts of data that we we use, and quite honestly, we typically haven't in the past used it all, so, because it was just too expensive, and so a lot of times we didn't use all our data. So when I first started at Hess, a long, long time ago, we worked almost everything on mainframe and plotters, so it was really a tedious process of running your job, getting a plot, analyzing it, making changes, making another job, running a plot, and it was very tedious and time-consuming. So, finally in about the mid to late 1990s, we started looking at Unix workstations, and we started deploying. They were very expensive. We started to deploy them in team rooms. They were so expensive you couldn't give everybody one, but they were very powerful, and you could start doing more interactive type work. As we got further into the 90s, we started looking at distributed computing. We started looking at kind of supercomputing, Unix-type supercomputers. They were, once again, very fast, very powerful, but they were no code. You had to write your own, so you had to do a lot of kind of coding and a lot of work. So it was very manually intensive, but very powerful. Another step in the right direction. And then eventually, as we started seeing the rise of commodity computing in Linux, we started to investigate that and started using desktop-type computers with open source systems and compilers, and we started to take that same kind of build your own seismic processing system from the distributed computing days, but we were able to reduce the cost significantly by using open systems and open software. Eventually, we saw the advantages to using the open systems, open source on the server side, so we said, well, let's start looking at it on the desktop side as well. So we started take that same kind of leap in performance and decrease in cost on the desktop. As typically happens in business problems, you solve one problem, you get another one that's more difficult. And as we started going, we were working really kind of a lot in the 2D realm. It was told that we needed to go into 3D, because 3D has got more detail, more accuracy. So to get to the 3D world, we needed very much a large-scale increase in performance. So we started looking at GPUs. We were kind of a pioneer in the use of GPUs to do computing. So instead of doing graphics, we were actually using them as computing engines. We were able to scale our performance up tremendously. Our cost per gigaflop dropped dramatically. And we were able to get into new phases of development. Another thing that we started noticing is once again, you kind of have these leaps where you got the desktop and the server, and then on the desktop side, the data once was getting larger, we needed more networking power, and so we decided instead of constantly having to rewire our building, we put all our workstations in the data center right next to the file servers, so we could leverage things like 10 and 40 gigabit Ethernet for our backbones and stuff. So that kind of was interesting because we took the computers away from our users, and who kind of were not happy about that. They really wanted to keep their computers. I don't know, it's just a computer, but they kind of got attached to them. But we had to come up with remote visualization technologies, which is interesting because it kind of was a precursor to the cloud as far as the computing is kind of remote to where the users are. They don't really see what is going on. They just have a desktop and they run their programs, and there's displays, but it's all remote. So kind of interesting. We kind of fought that battle kind of about 8 years ago. And then finally, it's HP Cloud. So as we started looking at cloud HPC, one of the real issues was how do we keep up? And so we'll kind of get into that a little bit later. But as we started looking at, we have these hundreds and thousands of computers in our data center. Well, who does that? Who can do that better? So, why did we actually start looking at the cloud? So I think most importantly, our executives said we need to look at the cloud. We need to put a cloud-first type agenda for going forward. So that was incentive. We need to start looking at it. We can't just ignore it. Also, on the HPC side, the computing requirements were growing dramatically. We were gonna if we kept trying to keep pace with all the growth, we were just going to run out of space, run out of power. we had to kind of make a decision. Do we want to keep fighting these battles or look for another way? Our product, the price of oil has dropped in several last couple of years. We didn't have as much capital to spend, so we didn't have as much money we needed to spend. So how do we get that performance increase without spending a lot of money? And like I said, once again, the exascale computing, which is the next paradigm, is really the domain of the large companies and the government. Hess doesn't really qualify as a super large company or the government, so we needed to look at something else. Also, storage. I mean, we've also, like I said earlier, we throw away a lot of our storage. We don't use it all because it's just too much. And then with data analytics coming forward, they want to use everything. They want to look at every bit of data. So we got to have more storage. And also, so either with storage, you can really either buy a lot of slower storage or a smaller amount of faster storage. So our plan was, let's try to go to the faster side. And finally, we really feel like we have lots of unused data on our system, a lot of cold, we call cold data, that we really could get rid of if we analyzed it and then move it somewhere cheaper. Oh, a second. So I think this is where I transition over to Sunny. He's going to talk about some of the kind of more general type trends.
Sure. Thanks, Jeff. So as Jeff talked about, the ever-growing reductions in CapEx in this industry, combined with the explosion in the seismic data for exploration, we really need to visit how the data is acquired and how the AWS can help accelerate that process. So this 80% figure is thrown out quite a bit. You see it here quoted by DJ Patel, who is the chief data scientist for the previous administration, in this book called Datadriven. So it's basically saying that 80% of the time, 80% of a data scientist's time is really spent on preparing the data for analysis, just getting it to a state where you can actually work on it. So it's even more with satellite and genomic data. It takes a lot of time and effort. We see this 80% as a huge opportunity. It's really about removing the undifferentiated heavy lifting. So what are all the things and the chores that you all have to do before you can actually start to do the work that differentiates your organization? And unfortunately, the problem is poised to get worse. As the cost of computing goes down, the cost of processing goes down, this allows us to put more and better sensors, producing more data, and at the same time, storage is getting cheaper. Unfortunately, bandwidth and networking are not increasing at the same rate. So what's the solution? If you look at this, sounds pretty simple, right? Move the data to the compute, essentially where you have virtually infinite compute. You look here with our Amazon S3, our simple storage service, our object-based storage, next to EC2, or elastic compute, where you can load your application and access them via the client. You'll see the code here for Paul Ramsey, creator of PostGIS open source project, where he talks about the time it takes to copying the data in a typical colo or an on-prem scenario. It's quite significant when you factor in terabytes and petabytes. What ordinary would take days or weeks now takes minutes and hours. So how do you transfer data in and out of the AWS cloud? So there's several options for moving data in and out of AWS. The right option depends on how much data you need to move, where you need to move, and how often you need to move. Of course, we will not cover all the services on the slide today. There's an entire storage track dedicated over the next few days. Feel free to check them out. This, as well as other sessions, obviously will be posted to YouTube and SlideShare as well for you to view later. But I do want to touch on a few that are relevant for this discussion now. First, internet. It's a potentially low-cost option. but it's a slow method of data transfer. It's well suited for small data transfer or sites where high bandwidth and low latency connections are available, and you've already invested in that. Generally, adding capacity is not cost effective for one-time data transfer, right? Second is AWS Direct Connect. Direct Connect offers improved network connectivity over general internet, but can be cost prohibitive or not available in all sites where data needs to be moved. Third, AWS Import-Export Snowball. It's the right data transfer choice if you need to securely and quickly transfer hundreds of terabytes to many petabytes of data to AWS. AWS Snowball can also be the right choice if you don't want to make expensive upgrades to your network infrastructure, frequently experiencing large backlogs of data, or you're in a physically isolated environment, or you're in an area where high bandwidth internet connections are generally not available, or they're cost prohibitive. AWS Snowball Edge is a 100 terabyte data transfer device with onboard storage and compute that you can use to move large amounts of data in and out of AWS. It's great for using it as a temporary storage for local datasets or to support local workloads in remote or offline locations. You'll hear from Jeff shortly on how his team used AWS Direct Connect as well as AWS Snowball for large data transfer. In fact, we claim to say that we've used the very first Snowball in the state of Texas at Hess. So when it comes to seismic data, we see customers dealing with acquisition, archiving, and processing. So first you acquire the signal data, pre-process and QA it in the field, and services such as AWS Snowball, Snowball Edge, and AWS Direct Connect can help there. Next, you have the archive data from vendors and upstream oil and gas companies such as Hess that are stored on tape and disk. And this is long-term storage. And you'll see services here that play a role, such as Amazon Glacier. You'll hear Jeff also talk about their archiving use case and how his team was able to take advantage of Amazon Glacier for several quick wins. Finally, processing their data with high-performance compute. Naturally, Amazon EC2 and S3 play a significant role there. So with that, I'd like to hand it back to Jeff to talk about their technical architecture and how the Hess team has made use of these services.
So we have an infrastructure at our data center in Houston, and we do a lot of work there, even today. Sometimes, we have more work than we can handle, or additional things we need to do. So what we do is we use the Snowball device, as Sunny remarked about, to transfer. We transferred a job recently. It was about 20 terabytes. That we wanted to get up within a few days to the cloud to do some testing on a new application where we're looking at. And so we used the Snowball to move the 20 terabytes very quickly. Didn't impact the rest of our company's connections to the cloud, but we were able to get it up there and moved very quickly and do our test. We would take that data, typically we put it in an S3 bucket, and then we would use various services from EC2 instances we would create on the fly when we needed them. We typically don't keep them running. We turn them off when we're not using them. Very, very easy. We turn them on real quickly when we do, and then we start running our job. And then, we also used the Direct Connect for smaller work, where it's not really necessary to go through all the effort to have the Snowball kind of mailed to us. We'll just send the data over the network and then run a quick job. We do that quite a bit. on some of our applications, some of our niche applications especially, we don't have a lot of need for them, but whenever we do, they're real important, so we want to run them quickly. So we'll use the direct connect in that case. But it's really kind of a nice model because you can use what you've got when you need more. It's there. You go to the kind of the nice web tool and you fire up your nodes. And either you can access your data through the direct connect, or if you have a quick turnaround or a small job. If not, you can ship it there. When it gets there, you fire up your nodes to do your work. One of the things that was initially very interesting to me around the cloud was this concept of archiving. Like I said, we have tons and tons of data in our environment. A lot of it we don't use, a lot of it, but it's expensive. It's very expensive to buy this data. They don't give it to you. You have to go buy it. So you really are hesitant to just throw it away. You want to keep it. So traditionally, we would use tapes. And what would always happen with tapes would be that 10 years later, you would need this data. It would be on some obscure tape you don't have a tape drive for anymore. So you'd have to scurry around, try to find someone who does have a tape drive, knows how to copy it for you to a new version. And it's just this endless cycle of, keeping track of tapes. They go obsolete. The drives need to be maintained. In fact, I think we still have a couple drives that we have in our data center that are almost 20 years old that we keep because we have this data that we have. And so it's really a pain to keep track of all these tapes. And because it was such a pain to do, no one used it. No one would archive stuff because they were afraid they wouldn't get it back or they couldn't get it back. And so what ended up happening was all the data that we had was stored on our very expensive storage devices. We don't really want to store unused data. We want to store our used data on our servers and our storage. And if we can minimize that, then we can actually maybe buy faster storage because we have less to buy. So I think archiving was really kind of a very important thing that I really kind of drove me a lot to looking at the Amazon or the AWS environment, especially with the Glacier. That was one of the. So this is kind of the workflow that we kind of developed around our archiving. So typically, whenever a project is complete, the users, they don't typically would want, they would just leave it there. And so what we've tried to do is try to say, hey, let's start identifying either milestones of projects or end of projects, and let's archive those as like a historical record, almost like what an archive is. So when we get the users, so the idea is we'll get users to file a ticket, which will get assigned to our team. We'll then run some software that we have that does some project-specific archiving, and then we'll kind of archive that project as a package. It'll sit on-premise on a kind of a caching device for 30 to 60 days, because I've generally found that when people archive things, it's with that kind of first month or two, they actually want it back most of the time. Once it kind of gets into the woods a little bit, it's a little bit less likely to get pulled back. But after 30 days, we'll then push it out to Amazon, an S3 bucket, and then we'll let Amazon manage the life cycle of it. So eventually, it kind of works this way through the Amazon life cycle and eventually ends up on the very low-cost Glacier storage. Excuse me. So I think I talked a little bit about some of the things we were thinking about. So we actually decided that we were going to do a project around cloud. So we kind of focused on two different efforts. We focused on the HPC, the high performance computing work that we were doing, and we also were looking at the archiving piece. For the HPC piece, we really wanted to look at, we had our own codes. We wanted to look at those. We also had vendor codes that we use for various algorithms and various programs. So we wanted to test both. We wanted to test on-premise versus public cloud versus hybrid cloud. We wanted to see what the various pieces involved with, especially the data movements. That was kind of my biggest concern, was moving the data around. How was it going to affect the jobs? We weren't going to do a lot of kind of deep kind of deep statistical analysis. We wanted to look at wall clock time. That's what the users care about. They care about how long does my job take to run. And for the archiving, really, we wanted to try various project level archiving, file archiving, Snowball archiving, various kind of ways to use it, just to see what kind of worked best for us. And so the results was very, very, very good. We actually found that functionally everything we tested worked. The results were exactly the same. They worked. No kind of issues along results. We did see that for larger jobs that the hybrid cloud just was a real problem. You could just sending lots of data. Either we would get the network team would say, hey, you're using a lot of the bandwidth, or it would take a long time. It would work, but it was just not optimal. We also tested both CPUs and GPUs, both on-premise and in the cloud. Once again, very much the results, the output looked exactly the same. There was no output issues. So we were very happy with good results. We were very conscientious about costs, because a lot of these things we were testing were using large numbers of very high-end instances, so they were pretty expensive. So you wanted to make sure you turned them off when you're done. So we were very conscientious about trying to watch our costs. One of the interesting things that we also found was we looked at kind of projecting out. We started projecting out our costs, and so we were trying to do an apples to apples comparison. So we said we have 400 servers and this many GPUs, and we would go to the Amazon calculators and we would say, well, how much would that cost? And then we started to realize, well, it looked very expensive. And then we said, wait a second. And then I kind of realized, I said, we're not really comparing apples to apples here. We had 400 servers of various vintages, whereas Amazon, you wouldn't need 400 because you would be using the newest vintages. So you were able to leverage, you could use a lot fewer servers and GPUs because you needed fewer because they were more powerful. So once we kind of realized that, we actually found that there's very interesting cost projections when you actually start looking at the apples to apples comparisons. For archiving, once again, it was just it turned out just to be a kind of a no-brainer thing. It just worked pretty well, whether we did Snowball or Project or whatever we used. We could get the data off into the cloud. The cost, especially of the Glacier, once we got to the Glacier, was just very, very nice. So it was just, it kind of was a no-brainer that we needed to be doing more of that. So this is kind of the recommendations that we kind of came forward with, is that and this is kind of what we have done, is that we should be using the cloud HPC resources for really small, right now for small to medium-sized work. We could do, things that can be done quickly using the hybrid cloud, and can be spun up and turned off very quickly. Needed almost no infrastructure from our perspective. For the larger jobs, one of the things that we need to do is we need to work with a lot of our vendors to help us, as somebody mentioned earlier, about getting the data directly to the cloud. We just don't want to be moving the data around. The Snowball is useful if you are going to put it there. It's going to be there for a while, which is not usually a problem, but if we could just have the data there to begin with, it would be really nice. And then once again, on the archiving side, we are really just, like I said, we're trying to really do a lot of work there and moving a lot of data to the cloud. So what happened after this was that we were actually able to retire a bunch of our computer systems that we don't need any longer. And by redoing that, we were just recently able to, with the cooperation of a lot of our colleagues, to kind of almost shrink our data center in half. And we've actually been calculating the power usage, and we've really decreased our power usage by half as well. We were able to retire about 400 servers, and And I think we're about 400 terabytes and growing of data archived to the cloud. And in next year's budget, I haven't put any money for new storage. So we're going to try to live with what we got. And so we're going to have to we have a lot of incentive to do the archiving. So what's next? So I think a lot of what's next is really kind of getting a lot of more of our applications in the cloud. We still have a lot of kind of desktop applications, and we still need to really work on getting a lot of that. It also works with our vendors. We need to work a lot. We use a lot of we purchase a lot of our software, and so we need to work with our vendors to get their software cloud enabled. And I think a lot of them see that that's the direction to go. So I think it's really not hard to press them. I think the biggest issue is kind of getting them all to work together. We need to, so one of the things we kind of talked about from the hybrid perspective, and kind of the real challenge is that you don't want the back and forth. You don't want to run one job on premise and then move the data to the cloud, run another job, then move the data back on premise, and then back and forth. It's just very expensive to move the data back and forth. So you really need to look at workflows and how you can optimize workflows to be cloud enabled. So not just the one pieces of it, but how do you get the whole thing, get the data, kind of a real optimized approach. Once again, the coordinating with the third-party vendors. Automation is really important. How do we get these nodes, they're very powerful nodes that we use. We really need to make sure when the job's done, they go off. We don't want to pay any more than we have to. But when we need them, they're turned on quickly. So we need automation through a lot of tools like CFN cluster, spot computing. So this is another thing. One of the ways to really get there's really two good ways to get the best price for Amazon instances. It's either to do reserved or spot. Spot's really nice because if you can quickly analyze what you need and go out there and bid for some nodes, it really gets you a really good price for the compute. It's a little bit challenging from the kind of, you don't have a true guarantee or knowledge of when things will be done or finished or whatever, but if you can leverage that, it really can save some money. We're also looking at things like containers and microservices. Once we get further, kind of further getting that piece of what you're using down further, more virtualized. We really are very interested in the concept of microservices, being able to kind of fire up these things that do very specific functions, and then concept of using microservices and data in the cloud and do a lot of work that we've traditionally done, kind of just have it kind of done automatic, real quickly. I think the other kind of fun challenge we have is the kind of the cultural and environmental challenges. I think there's still, how do you get the buy-in? I think from an executive perspective, we've always had really good support from an executive perspective, but getting the users, to understand the direction. It's a bit of a challenge. I think there's a little bit of, unknown about the cloud. I tend to think, in a lot of cases, I think the world that we've been in has been kind of cloud-like for some time. I just don't think people called it that. So I think as people start seeing things are a little different, and you start seeing some of the benefits that will be kind of overcome. With that, Sonny and I would like to thank you guys for coming to our talk today. And if you have any questions, we'll be glad to take them.